this lecture, the final lecture for Chapter 16, what we're going to look at is how we're going to implement a set data structure. Now, previously in this chapter, we looked at how to implement a list data structure, and we implemented a list data structure with a linked list, and we showed how you could also implement a list data structure with an array list. Two different implementations of an idea for a data structure called a list, and those two different implementations, the array list and the linked list, had different kinds of behaviors. Then we also looked at how we might implement a stack. And we said that, well, if we have a linked list, we can implement a stack, because someone who uses a stack expects the methods push and pop to work. And we can build a method push and pop using a linked list, and instead of using push and pop, we'll use methods like add first and remove first in order to make an efficient stack. We looked at how you could do the same thing with a linked list or with an array list. We looked at how we could make a queue and we could back it with a linked list or an array list. We looked at how we could make a back the queue with a circular array as well. So we looked at several different things that we would like to provide, several different data structures that we would like to provide the user, and several different implementations of how we might implement them. And today we're going to continue that pattern by looking at how we might implement a set using the data structures that we have available to us. So first, let's motivate this by a little bit of code. On the left over here is some code that a user might use in order to implement a set. Now, in this code, an API programmer needs the ability to keep some data in a set. The data that they're keeping in the set is going to be strings. Remember, a set is an unordered collection of unique elements. And so if we put more than one into it, it's not going to produce the same data. It's not going to keep more than one in there. And also, the order in which the user puts things in is not necessarily the order in which they're going to get them out. That's not one of the contracts of a set. All right, so now in this example bit of code, to make it clear, to motivate this assignment, to motivate this lecture, I called the set my HashSet. Now, when you use the data structures that are provided by Java, you won't use that name. You'll use something called HashSet, or maybe you'll save it as an interface set. Now, in the rest of this lecture, and in the textbook, they talk about implementing HashSet. Now, we don't actually need to implement HashSet because that's provided for you by Java. But as computer scientists, we want to know how it's implemented so that we could use that same technique to implement something else, and also so that we understand what's efficient and what's inefficient about using a set. Okay, so my HashSet is my implementation of the HashSet, and this is how someone would use it. First of all, we need to create a variable of type my HashSet. In this case, it's called names. And we're going to initialize it by calling a constructor for my HashSet, and we're going to pass it the parameter 101. Now, this is a parameter that says how big of a hash set are we going to use. In a fully developed hash set, like the one that Java provides, the size is managed for you, much like an array list manages its size for you. Then we're going to take that names variable, and to it we're going to add several different strings into our set, our collection. We're going to add the string Harry, Sue, Nina, Susanna, Larry, Eve, Sarah, Adam, Tony, Catherine, Juliet, and Romeo. And so after adding all those names, we have one variable names that contains that collection. Somehow, my hash set is keeping track of all of those. Now, if we call names.remove Romeo and names.remove George, based on how we understand a set to work, we would assume that those names have been removed. Well, how are we going to implement that in my hash set? That's the focus of this lecture. Finally, something that we have to talk about is how we might provide an iterator so that a user can walk through all of the elements that they've stored in their hash set. So in this case, my hash set provides an iterator. The way you get it is by calling names.iterator. And that returns an iterator. In this case, we gave it the variable name iter, short for iterator. Once we have that variable, which we've written an implementation of an iterator in order to support my hash set, the user can call while iter.hasNext and one by one get the elements out of the set. For example, iter.next. Now if we run this code, what we can see now over here on the left, if my green screening goes right, is we can see a list of names that have been outputted by our set, and they're the ones that we expect to be there. So we see that Sue, Harry, Nina, Susanna, Larry, Eve, Sarah, Adam, Juliet, Catherine, and Tony are the ones that remain in our set after removing Romeo and George. And if you look back at our code, you can see that that seems appropriate. Now notice that the first name that we got from our iterator was Sue. But if you look at your code, the first thing that we put into our iterator was Harry. So in that sense, our set is keeping track of everything that's in our set, but it's not keeping track of the order in which we put it in. Because it's not keeping track of the order, it can be more efficient than a list is. Okay, so that's our motivation. We want to provide this kind of interface for our user who would like to use my HashSet. So now let's walk through the different things that we need to understand in order to implement this. So for that, we're going to switch to a different set of slides. Okay, so we are going to do the work of implementing our HashSet, which is a kind of a set. In order to implement our HashSet, we're going to use a technology called a HashTable. Now, in the Java library, the interface sets, you can choose to implement them with a hash set or with a tree set. This is similar to the way in which you get a choice. When you want to use a list, you can use an array list or you can use a linked list. So when we talk about implementing the hash set, we're talking about one possible implementation of a set interface, the hash set. All right, now a fundamental aspect of using a hash table in order to implement our hash set is that we need to understand what hashing is in a computer science sense. So in a computer science sense, hashing means to place items into an array at an index determined by the element that we're putting into the array. In order to find that index, each thing that we put into the array has to have a hash code. What you should think of when you think of a hash code is you should think of it as like a fingerprint of the data that's being stored. And the format of the fingerprint is as an integer. So what do I mean by that? I mean that every class that you implement, whatever the instance variables are set to within that class, and whatever other data you've got in that class, if you want to produce a hash code, that data instance has to produce a number which is unique to that particular instance of an object. Just like a fingerprint is unique for each instance of a person. So we need to create a hash code for our data. And we want the function that produces the hash code to do it in such a way that different objects have different numbers. Now, have different fingerprints. Now this isn't possible because it's not possible to guarantee this. And so occasionally we'll have something called a collision. And a collision is when two different instances of an object have the same hash code. When two different instances of an object can be hashed, and that generates the same integer. So when we create a function that calculates that fingerprint, we want it to do it in such a way that we get very few collisions. A collision would be like two people having the same fingerprint. We want it to be rare. So a good hash function is going to minimize these collisions. Now, assuming that everything that a user wants to put into our set can be hashed, we can get a fingerprint of it, we can use that fingerprint in different ways. For example, we can use that fingerprint to identify where we're going to store an element in an array inside our hash set. Let's look at this in a little bit more detail. Here are some examples of what I'm talking about. This is a table in which the data that the user would like to store in the set are strings. So several different strings are listed here in two different columns. We've got strings that start on the left with Adam and end on the right with, looks like VII. Each one of those strings can be hashed to give us a hash code. And those numbers are listed down the right columns next to each one of the strings. You'll notice that they're integers, and you'll notice that sometimes they're negative integers. It's a fingerprint, it's a unique integer, and that's a function of that we can write a function that takes in a string and returns a hash code. Move right. Okay, so our hash table, the technology that we're using to implement the HashSet, which is an implementation of a set, our hash table is going to be an array. And that array is going to store the elements that the user wants to store in the set. The user's not going to know about the array. The array is just going to be a tool that we use in order to create this illusion of a set. The hash code, the fingerprint that we take of the elements that the user wants to put into the set, we could imagine just using that as an index into the array. So a very simplistic implementation of a hash table would be to have a very, very large array. In fact, an array that has one element for every possible hash code, meaning one element for every possible integer. That's an awful lot of integers, and it's a very large array. But if we think about this just abstractly, whenever someone wants to put something into our set, we could take that element, calculate its hash code, go to that element of the array, and store that element there. In that way, it would be very easy to locate an element. If we want to know where it is, we hash it and we look in that location. It's like we have a bunch of mailboxes and we want to put a piece of mail into the mailbox, and we can do something to that letter, that envelope, that'll give us the number that we're supposed to put this letter in. It's a very similar idea. Now the thing is this simplistic implementation is not practical. Because in order to get an array so large that there's an element for every possible fingerprint, we would have to have an array that is as large as the largest integer that we can represent, times 2 because we can go negative. That's a complication as well. That's too big. And so we need a different way of handling this. Move right. What we'll do instead is we'll use the modulo or remainder operator. And in this way we can have a reasonable sized array but still use the hash code in order to identify which bucket we're going to put it in, which slot in the array. So what we'll do is any time that a user would like to put something into our array within our HashSet implementation, we'll calculate the hash code by asking the element x to give us its hash code. Strings have this built in. We'll store that hash code or that fingerprint in the integer h. We'll make sure it's positive by very explicitly asking if h is less than 0, then we'll take the negative of it, so a negative number becomes a positive number. And so after that second line, we know we have a hash code and we know it's positive. To locate the position in the array that we want to put that element, we're going to take the full integer and we're going to take the remainder after we divide it by the length of the array that we have. Now that's interesting because what we're keeping is not the number of, not how many, not the divisor, not the result of dividing, but the remainder afterwards. So we know that position is going to be some number between 0 and array length minus 1 inclusively, which is perfect because those are exactly the indices that are available to us for an array of length, array length. Okay, so that tells us that if we have an array of a certain length, we know where to put a certain element when we want to store it there. Now, how do we deal with collisions? What do we do if we take one element and we put it into an array, and we get a second element, and it is different data, but it has the same fingerprint, and it needs to go into the same slot? Well, there are different strategies for dealing with this problem. This problem is called a collision, when two hash codes for different elements map to the same element in our hash table. One strategy we can use is called separate chaining. And what separate chaining means is that every time we get something that goes into a particular slot in our hash table, instead of storing the elements there directly, we'll store a small linked list or a chain of nodes that starts from that element in the array. And so if something's already there, we'll just put it at the beginning of that linked list. And if nothing's there, we'll start a linked list with just that element. That way, each entry in our hash table points to a chain of nodes that contain all of the elements that the user has put into our hash table, into our hash set, that have collided. Now hopefully, if we've done a good job of writing our hash code function, it will be rare that we will put things on these chains. So what we do is in our hash table, we call each one of these entries a bucket, because each one of these entries can hold several different data elements at a given time. They hold sequences of nodes that all have the same hash code. Move right. If you want to think of a metaphor for this, you can think about a farmer's market, where there's several different buckets that are laid out, and in each one of those buckets, different produce is placed that has the same fingerprint, or that belongs in the same bucket. So a bucket of chili peppers and a bucket of tomatoes and maybe a bucket of walnuts or whatever you're selling are all going to be put in the same location. And so if you want to go look and you want to ask the set, do you contain a walnut, you know exactly which bucket to look in. If there's walnuts in there, you have some. If that bucket is empty, you know that you have no walnuts because that's where walnuts are stored. Walnuts aren't stored anywhere else. It works the same way with the bucket. Elements with the same hash code are placed in the same bucket. Move right. All right, so now we have to implement some of our functions that a user might want to use when they have a set. Some of the things that we saw the user using in the very beginning of this lecture when we saw how someone might use our hash set. So one thing they might want to do is they might want to know if our set contains an element or not. Okay, well here's an algorithm for how you can go about finding whether your hash set contains an object. First of all, you ask for the fingerprint of the object that you're looking for. That's going to give you the hash code that you're interested in. Then you compress it. And by compress it, I mean you use the remainder operator, the modulo operator, to figure out not which integer bucket it belongs in, but which of those smaller number of compressed buckets it belongs in. That's going to give us H, an index into our hash table. Now we go to that location in our hash table and we look to see if there's a chain of nodes there. If there's nothing in that element, if there's nothing in that entry in our hash table, then we know that our set does not contain the object that the user asked for. Just like if we find that our bucket of walnuts has no walnuts in it, then we've got no walnuts. If it turns out that there is a chain of nodes there, we don't know for sure that it contains the object that the user asked us to find. And that's because perhaps there was a collision and other elements are also in this bucket. So once we find out what bucket we're in, now we walk down this chain of nodes asking each one if it contains the object that we're looking for. If it does, we stop and we return true. If we get to the end of that chain and it's not present, then we stop and we return false. So either the match is in that chain or it's not. Now the efficiency of this is very fast, because if we assume that there aren't very many collisions, then it's basically constant time, because all we have to do is calculate our hash code. We assume that that's a constant amount of time, and then we go directly to the bucket that we're interested in, because we're implementing this with an array, not a linked list, an array. So we can go directly to the bucket we're interested in, and then when we look to see what's there, the length of our chain has a limit to how far it can be. And if you read in the textbook, it'll give a little bit more explanation of why there's a limit to that chain length, and therefore why it's a constant time overall. Move right. All right, now we might be interested in adding and removing elements. Well, once you understand how you find whether an element's present or not, adding or removing an element is a very simple addition to that algorithm. So again, a user would like to add something to our set. We don't want to add duplicates. That's the main thing that we've got to tackle here. So we take the parameter that the user has asked to add to our set, we calculate the hash code of it, we compress it, take the remainder of the array length, and that gives us our index H. We now go to that bucket in our array, and we walk down our list to see if the element that we want to add is already present. Ask if it's contained. If it's already present, then we just quit, and we're done, because it's already in our set. If it's not present after we get to the end of that bucket, the chain in that bucket, then we add the node to the beginning of that bucket, which is a very fast operation because what is stored in our array is a linked list. All right, so great. We know how to add an element to our list. Removing an element is very similar. We receive the parameter of what we would like to have removed from our array list. We walk down the list. If we see it, we remove it just like we would remove anything from a linked list. And if we get to the end of that linked list and it's not present, well, fine. The user asks us to remove something that wasn't in our set in the first place. And again, this is also a constant time operation. Now, the reason why we specify that it's a constant time operation with that little footnote, that plus, is because just like when we're growing an array inside an array list, if we find that our buckets, our hash table, have lengths of chains that are too long, if we have too many things that are stored in too small of a hash table, then we have a one-time operation where we double the size of our hash table and fix all the elements that are already present in our table. We don't have to do that very often. We just have to do that if our hash table gets too full, just like we had to do it for an array list if our underlying array got too full as well. Move right. So removing, like I said, is the same process. We take the element that we want to remove, we find the hash code, we compress it, that gives us an index H. We look in our array, we walk down the linked list. If we find the element, we take it out of that linked list. And if we don't find that element, we just return because we don't have to worry too much about it. We don't have to worry about removing something that's not there. Just like we can grow an array, if we remove something, we might also want to consider shrinking the hash table. And shrinking the hash table is an important way in which we bound the running time of this algorithm. So again, just like adding an element is constant time, removing an element is constant time as well, with a little footnote, because occasionally we need to shrink the size of our hash table to keep our operations efficient. Move right. Finally, we need to provide a way for our user to iterate over our hash table. And so that means that we need to implement an iterator. So our iterator is a little bit tricky, because what an iterator has to do is it has to be able to walk through all of the elements that are in our hash table, and they have to produce them one at a time. Going through all the elements that are in our hash table is a two-step process. First of all, we have to go through bucket by bucket and walk down the buckets as the user calls next. And then when we're currently located at a bucket, we have to walk down the chain in order to make sure that we see everything that's in each bucket. So when an iterator points to the middle of a node chain, like if an iterator is already walking through and the user calls next on it, we need to step to the next node in the chain. But if we get to the end of the chain, we need to step to the next bucket. And so because of that, the iterator has to keep track of what node it's on, as well as which bucket it's in. And then also just skip over empty buckets. Here's the guts of the code that gets executed when we call next on the iterator. What we do is we ask if the current node that we're pointing at, if it's not equal to null, and the next element is not equal to null, that means we're in the middle of a chain and we're walking down the chain, then we say the next element that we want to return is, we have to walk down that chain. So we say current equals current.next. If we're either at a bucket that has no nodes in it, or we're at the end of that bucket, then instead what we do is we increase the index of the bucket we're looking at. And then we check to make sure if we haven't walked off the end of our array. And if we are, then we just throw this exception and say, hey, we're done. We've gone through the entire array. Your iterator has no more elements. But if there are more elements, then we start walking down the chain by saying current equals buckets sub buckets index. Move right. This is kind of a visualization of what's happening when we do our iterator. So we provide our iterator to the user when they ask for the iterator, and we initialize it so that the first bucket it looks at is bucket 0. And we walk through until we find a bucket that has something in it. So in this case, we end up starting our iterator at bucket 3 and starting our current node at that first node. Well, when we call next, we move our pointer from the first node in bucket 3 to the second node in bucket 3. If we were to call next again, we would iterate our bucket down so that we would walk our iterator down to bucket 6, and point current to the first node in bucket 6. Move right. The efficiency of the hash table is something we care a lot about. And one of the things we find very powerful about the hash table efficiency is that it's very constant time. It has a lot of important constant time methods. The cost of iterating over all elements of a hash table is proportional to the table length, not the number of elements in the table. And so we can shrink the table when the load factor gets too small. The load factor is what percentage of our table is full. And one iteration is going to be constant time. Iterating over the entire table is going to, of course, be order n, or the number of things that we have in our set. You know, if you're going to look at every element in your set, you're never going to be able to do better than the amount of time it takes to look at every element in the set, or order n. But finding an element is constant time, because when we take that fingerprint, we know exactly where to look. And adding or removing an element is constant time, as long as we don't have to grow or shrink the array, because we know exactly where to look. And iterating through all our elements is about as small as it could be, which is order n. So we like our hash table because it's very efficient. So let me stop there and give you a chance to reflect on some of the ways in which a hash table can be used and some of its properties. A little bit more elaboration is given in the textbook to describe ways in which other ways of dealing with collisions and a few other different alternative ways of implementing the hash set. Thank you for your attention.